We are very fortunate to have Mike Shepard here with us, talk about a survey of M-class asteroids, results from the last decade. Mike Shepard is a professor and chair of the Department of Environmental, Geographical, and Geological Sciences at Bloomsburg University of Pennsylvania. Over the past 2 decades, he's used the Arecibo radar telescope to study the M-class asteroid population. He used multiple data sources to generate the 3-dimensional shape model of 16 Psyche that's currently used by the Psyche mission, and an updated shape model of the dumbbell-shaped 216 Cleopatra. Thanks so much for being here with us today, Mike. I'll turn it over to you now.
Thank you very much. Let me start my thing here and start sharing. So share that screen and start this. All right, can you see that? Should be some rotating asteroids.
Looks good.
Okay, great. Well, first of all, thank you for inviting me. I just want to start out by saying I feel kind of like an 18th century naturalist. We're living in the golden age of planetary exploration. And in my lifetime, we went from having no spacecraft to no planets to spacecraft to all the planets, including orbiters. And we're just now, getting to the point where we're starting to look at the asteroids a little bit more in detail. And it's an exciting time to be a planetary scientist. So a significant fraction of my work has been on the M-class asteroids, and I've been doing it for about 20 years. So I thought I would share, I don't know if we'll come to any conclusions, but I think we can put some constraints, or at least put some interesting data points in place for you to keep in mind when we try and understand what these objects are. On the left is the newest Psyche shape model that we published last year. It's a little bit thinner in the C-axis than the one we published in 2017, and I have an albedo map painted on it, which was published by Vikunkowski et al. And I'll explain that more in a minute. And then on the right is Cleopatra. This is the classic, was a dog bone asteroid, but since that first shape model was published by Steve Ostro in the late 90s, we obtained several new data sets. And so I tackled that in 2017, 2018, and published an updated model of it. So very intriguing M-class asteroids. So just a brief outline, I thought I would start at the beginning. How are the M-class defined? And X is a synonym for M in many cases. And then just a very brief overview of how we think they formed, what we think they are. There's a lot of ideas. And then the bulk of this is going to be looking at some updated characteristics and correlations. I'll look at the numbers, the sizes, the classification, spin rates of these objects, and then I'll spend quite a bit of time on the radar characteristics, which is what I've focused on the last 20 years. I'm going to point out specifically one piece of the radar characteristics, bifurcated radar echoes, and I hope explain that a little better when we get there. And then I'll look at the characteristics of a few specific asteroids, which are kind of some in members, and in some cases ones that we're very intrigued by because we're going to go see them. Finally, I'll end up, what, if anything, can we deduce from all of this? So I'll start with the definition. The M-class were originally defined by Tholen. So the first asteroid classifications were put in place when I was a teenager, and that was basically a C and S class. And then Dave Tholen did his PhD thesis on this. I think it was published in '84 or so. And by that time, there was enough multicolor spectra of asteroids to start to look for patterns. And so the classical Tholen taxonomy was born. The ones we're focused on here are the EMP class, and I've highlighted them in red over on the right. And they are defined as generally featureless spectrum. These are optical spectrum with a reddish slope. And they sometimes have subtle absorption features. The only problem when Tholen looked at these was that there was a variety of asteroids that had this kind of spectrum, but they differed wildly in albedo. So he subdivided them into the P class, which are the darker and more primitive objects, thought to be more primitive, the brighter ones, the E class, with albedos, optical albedos greater than 0.3, and then the M class kind of fell in between. And this was consistent with laboratory analogs, spectral analogs that included the iron meteorites, instantite chondrites, some of the high iron carbonaceous chondrites, the CB, CH classes that we have been intrigued the last few years, and then the Mesociderites, and I'm sure there are others as well that I haven't mentioned, but those are the big four, I guess, that have been used as possible analogs for this class of asteroid. Then in Bobby Buss, I think also for his PhD thesis, took advantage of a plethora of new observations from specs at the IRTF, and keeping most of the traditional Tholen classes, but expanded on it. And so developed this new taxonomy called the Buss taxonomy, or if you look at it in some references like the JPL Horizons small body browser, it's called the SMAS 2 classification for the survey that was done as part of this. There's no albedo information in this classification. It was strictly based on the shape of the spectra, and it was limited to the visible and very near infrared. And I forgot to mention in the Tholen taxonomy that there were no albedo information. The EMP were just called X. The X class was anything that was EMP-like with no albedo. So Buss kept that, and everything is now an X class in that scheme. And then he subdivided that further because there were more classes or more spectra available with subtle differences, and the subscript indicates a transitional spectrum between the X class and whatever was indicated. So an XC was transitional between the X and the C class. And then Francesca Di Meo, a few years later, I'm not sure if this was a PhD thesis or just something shortly after, but kind of extended the Buss taxonomy, this time by including the infrared or near infrared from about 1 to 2.5 microns, in addition to what Buss used in his taxonomy. Kept essentially the same classification scheme, and I've highlighted them over on the right. What she found was that there was quite a bit of overlap with the C complex. So the Cs are also, often featureless. And there's at least one asteroid I'm going to show you that I'm calling an M, but in this taxonomy is called a CB class. Very intriguing one. So this is where we are, mostly featureless spectra, ambiguous, difficult to pull out kind of the spectral features that might tell you what they're made of. And these, I'm just going to show you a couple of examples of things that have been done recently trying to match these. So the Rosetta mission flew by Lutetia, first M-class observed by spacecraft. And the blue line there, which is got the arrow pointing to it, is the Virtus. That's their visible infrared spectrometer on board that spacecraft, is shown fairly featureless, a little concave. And then a number of analogs that have been proposed for these, including the CO, CV chondrites, CH, CK, Es. And I think their conclusion in that paper was that it was more consistent with the instantite chondrites, or possibly those high iron carbonaceous chondrites. But it wasn't conclusive. This is a recent paper by one of Vishnu Reddy's graduate students, where they mixed carbonaceous chondrites and low iron pyroxenes with metallic end members in the laboratory to try and duplicate the Psyche spectrum. And so this is just the metal end members that they've done, and they did a series of these mixtures. And so this is one where they've added some percentage of carbonaceous chondrites, and then in others, if you look at the paper, you'll see the variety that they get, each one trying to tweak it a little closer and match the spectrum. So these are all efforts that have been made to try and figure out what exactly is on the surface. I think most people would agree spectrally there's a good case for metal, and then silicates are a more recent addition to what people have believed to be on these asteroids as well, but it's mostly low FeO stuff. There's not a lot of absorption features in them. And then a very intriguing finding that came out, early 2000s, the discovery of water of hydration, or I guess hydration features, OH absorption features in the spectra of a number of M-class asteroids. And Andy Rivkin, I think, did the most amount of work on this, where they kept looking at the M's and finding these. These are difficult measurements to make because there's a lot of atmospheric water that has to be subtracted from the spectra. And so they used the higher TF, which is pretty high, and so there's a very low water abundance up there, but still it requires subtracting the continuum and then some massaging. But these features here were observed by Idris Takir, one of a colleague of mine. Actually, I'm a co-author on this paper, when we were looking at Psyche a few years ago. So Psyche also appears to have this feature. And I'll show you in a minute a plot of how many of these asteroids, the M-class, have this kind of feature. That it's not traditionally thought to be consistent with the formation for most M-class models. Hydration is typically associated with the more primitive classes. So I think most people have become comfortable with the idea that this feature is due to external, additions later to the surface of the asteroid. Although there are some interesting hints in one of Lindy's recent papers that possibly some of these came from the outer main belt, and maybe hydration is internal. So very briefly, I'm just going to show you some of the models that have been proposed for the M's. This is from a recent paper Lindy Elkins-Tanton published, Distinguishing the Origin of Asteroid 16 Psyche. Very good paper. A lot of interesting stuff in there. And what you're seeing at the top is what they're calling the fiducial hypothesis there, I guess, zero order. This is what they're going in expecting. Psyche is in part a metal core, but it's a differentiated body with largely a chondritic outer mantle crust and then a metal core. The outer part, which had higher iron oxides and more absorption features, was stripped in a number of impacts. And what you end up with is the remains, which is the lower FeO mantle-ish material, and then regions where you may have exposed core. I think that's probably a really good model for what they might find. And then the other one is that Psyche is some kind of undifferentiated chondritic object. And then the analogs we mentioned earlier are still mentioned here, the instantite chondrites or the high iron carbonaceous chondrites that are a possibility as well. Another one I'll mention here, I saw Alan Rubens here, and this was a paper he published a number of years ago, the Mesociderite parent body kind of model, where you didn't just have a hit and run stripping off significant portions of the outer crustal material of a parent body, but you had a complete disruption and then reassembly. And so the surface would be a mix of silicates and iron material. And in the past, this has been proposed as a possible source of the Mesociderite asteroids. And then one I'm particularly intrigued by was only recently published. This is by Johnson. There was another one, a slightly different version, but in essence, this model says that Psyche and other similar sized M-class asteroids were differentiated, but they contained a high amount of volatile sulfur types of materials, which allowed their iron to stay liquid much longer, and that you had these eruptions onto the surface. You would have to have a thinner mantle, and it might be more preferentially found in low regions, places where there were impacts. But it reminds me of the mantle, or I'm sorry, the Mare model for the moon. So this is the ferrovolcanic model for Psyche, and so you would have places where these eruptions in place, preferentially iron-rich lavas. And this is just another figure from that paper, which is being used to kind of show you how thick the mantle would have to be. So it's primarily a large core that remains, existed at the beginning, and then your mantle can be tens of kilometers thick, but it would depend upon its density, and then ultimately the density of Psyche as a whole, which has been a moving target, but I think the consensus has settled down to somewhere around 4,000 kilograms per cubic meter, which is roughly halfway between. It's higher than rock or chondrites, but it's considerably less. It's half of what you would expect for a pure metal object. So just looking at some numbers and gross properties of the M's, how many are there? I did a JPL small body database search. So if you find all the Tholen classified asteroids in the database, and it's a simple, Tholen is defined when you do the search. There are 980 Tholen classified asteroids in the Horizons database, and of those, 38 are classified as M, so they were originally classified that way. And then 10 are Tholen X class, which at the time meant they didn't have an albedo, but subsequent information for those 10 X class asteroids has determined they have albedos between 0.1 and 0.3, so they would fall under that classical definition. So that's about 50 out of 1,000, or 5% of the Tholen, of the asteroids in the Tholen classification scheme are M class. If you instead use the SMAS 2 classification, which is also in the Horizons database, there are a little over 1,600 asteroids with that classification. And if you look for the X, the XC, XE, and XK, and then if you limit the albedo to 0.1 to 0.3, you get about 100 main belt asteroids. And this is roughly 7%. Now, I know some of those main belts and near Earths that come up are not M class. In fact, Rosh Shalom came up in that search, which is one I worked on years ago, which is, I think it's a K class, but right now it's classified as XC. Nevertheless, if you look at these two together, you can come to the conclusion that the M class make up roughly 5% of the main belt population. I put this graphic together just because I wanted to. I thought it was kind of cool. I took the 10 largest M class asteroids based on their current sizes anyway. Two of the shapes I generated, so the one in the middle, Psyche, is the most recent Psyche shape model. Off to its left is Cleopatra from our most recent Cleopatra shape model. Then you have down in the lower right, lower left is Lutetia, a picture image, a classic image of taken by Rosetta. The other shapes, with one exception, have all been generated by light curve inversion. So the Joseph Durek has this DAMIT website, DAMIT, which is a great website. They've mastered the art of taking lots and lots of light curves and inverting them to generate convex shape models. And then in a number of cases, they have applied adaptive optics images and occultations, and will also generate alternative convex shape models. So the Antigone model over on the far left is one of those. But you can see there are not very many larger than 100 kilometers. So if you look at the diameters published for all of these 100 or so M-class asteroids in the database, you see that vast majority are smaller than 100 kilometers. And I've color-coded them. 2005, Bill Botke published a paper that suggests that things larger than 100 kilometers are more likely to be primordial than not, and things less than that are more likely to have been collisionally evolved and not primordial. So there are only a few, handful that are bigger than 100 kilometers in this entire group that we know of, including a number that are quite small. If you just look at the ratio of the different X classes in the SMAS scheme, you see that there's roughly equal amounts of X and then others. So the XC, XE, and XK combined roughly equal the X's. And I took anything that was classified only as M in the Tholen database. If it didn't have an SMAS classification, I just gave it X. So That's one little caveat to this figure, but I think the conclusion still reasonably holds. And this is a plot I'm sure many of you have seen. There seems to be a high number of rapid spinners in the M-class population. I've heard different ideas for what that is, but I think that still has yet to be determined. So it's a curiosity that I think exists primarily in that class. That's whether it's related to what they ultimately are or not is an interesting question. So now this is what I'm about to show you is work that I did, and I saw that a number of people I've worked with are here from Arecibo. Patrick, especially I see Patrick's here. So for 20 years, we systematically observed all the M-class asteroids that came within the beam of Arecibo. So, you have limited pointing. You had to be a little serendipitous to get an M-class in the beam. And then it also had to be big enough. And you had to be able to get the time. So, there are a lot of challenges, but we managed to get about 30 of the entire population over that period of time. And so what I'm going to do now is show you the results from that. Most of this was published in 2015, but there's some changes to my thinking since then. And of course, we lost it in 2020. We were going to be, hoped, observing Psyche again, but unfortunately, the collapse, took place. And so right now, I would just mention this is the only facility in the world capable of doing what we did. Goldstone exists, but Goldstone, on its best day and the best configuration, could only get a low SNR echo from Psyche and maybe a couple of the others, but it doesn't have the power or the sensitivity to do what we did here. So they can replace Arecibo, or I understand that Patrick's working right now to do some kind of a joint thing between Goldstone and on addition in West Virginia, which escapes me, the Bird Telescope, some kind of bistatic array. We might be able to get back to doing some of this. So this is an updated version of the final figure from a 2015 paper. So it's going to take a little bit of explaining. So give me I'll ask you to bear with me here a minute. So every asteroid that we observed is along the bottom. There are 26 of them here. Actually, we observed a few others, which I didn't include because later we found out they fell out of the M class, including 83 Beatrix. It's too dark. On the left is the radar albedo. And this is just an analog for the optical albedo. The higher the number, the more radar energy is reflected back to the observer. Chris Magri did a couple of survey papers a few years ago for all of the observed main belt asteroids, and statistically, grouped them and found that the mean S and C class asteroid, which are the bulk in the main belt, had radar albedos of about 15%. So between 0.09 and 0.19 covers their mean and one standard deviation. Then what I'm calling high metal, so that's the blue region there, shown down here with the mean S and C. This peach colored, I guess it's peach colored, is where we find the bulk of the M-class asteroids, and I'm referring to it as high metal. It's an inference, but I think it's a reasonable one. And then this region in between is kind of a no man's land between the S and the M classes, what I'm calling moderate metal. Now, I also have some numbers over here. Steve Ostro and others published, there are a couple of models out there for turning a radar albedo into an estimate of the bulk density of the upper meter or so of regolith of an asteroid. So I adopted a couple of those and published sort of a joint model. And so these numbers are rough estimates, but they seem reasonable. And so I put them here for you to see where we're thinking. So the lower end of the mean S and C class suggests regolith with a bulk density of 1.8 grams per cubic centimeter or so, whereas the S and C class, the upper ends, are bulk densities of roughly 2.5 grams per cubic centimeter. So that's probably consistent with, regolith of 40% porosity, maybe 50%, and then at the upper end, certainly some metal concentrations that you would expect from, ordinary chondrites or other analogs for the S class. At the lower end of the radar, a high metal up here, 0.3. The model suggests bulk densities of around 3.5 grams per cubic centimeter. And at the upper end, around 4.5 to 5 grams per cubic centimeter. And these you would only really achieve if you had a significant fraction of metal in the regolith. You might also get something around 3.5 if you had a solid object, but that's considered unlikely for a large asteroid. It might be possible for one of these monolithic near Earths, but for the larger main belts, we're assuming that there's some kind of regolith, and it's probably got a bulk density of, like we said, 30 to 50% or something. The red dots are the mean radar albedos that I observed for all of these over, in some cases, multiple apparitions. And then what I've posted on this that's not in the original figure are these lines that go up. So in many cases, we saw a lot of variation in the asteroid radar albedo as it rotated. So the line there represents the range of from the mean to the max that we observed in these asteroids. So Cleopatra is it's got a high radar albedo anyway, of around 40% or so, but then there were aspects of it where we saw radar albedos go up to 70 to 75%. Psyche, its mean radar albedo has dropped over the years as we've gotten more and more observations, but at its highest, even area corrected, we're getting radar albedos of about 50% or more. So in total, you can see that a large number, roughly half of the targets we looked at, fall in this, what I would call high metal range, certainly 2 to 3 times more bulk density than you get from your typical main belt asteroid. And then the rest of them are either in this no man's land middle region, which I'm calling moderately metal rich, and or the upper end of the mean SC class. I'll come back to Calliope. It's kind of an outlier that we'll talk about in a minute. If you look for trends with the radar albedo and other properties, the first one you might think of is optical albedo. So this is the mean optical albedo published in the Horizon database versus our radar albedos, and there's no obvious trend here. It's kind of all over the place. If you look at the SMAS classification, again, the sample is pretty skewed. We mostly looked at just X class. There were a few XC, XE, or XK asteroids. Nothing obvious stands out here, and I did put the CB down here, which is radar bright. The blue is what I'm calling radar normal, or it's elevated with respect to the S and C class, but it's still less than what I'm calling radar bright. If you look at the radar albedo versus effective diameter, there doesn't, again, seem to be any obvious trends. Psyche is the only one sitting out here at this range, but the remainder, you can't really say much with statistics of 2 or 3, but there doesn't seem to be anything really obvious here in terms of which ones are bright, being bigger or smaller. And finally, although you have this big spike in 4 to 6 hour periods in the main M population, there doesn't seem to be any real correlation between the period of the asteroid and whether it's radar bright or radar elevated normal, whatever you want to call it. Again, the statistics, samples of 2 and 3, it's difficult to say anything convincing, but this looks pretty random to me. And then finally, this was something we pointed out. If you look at the hydration state, which of those asteroids have an OH feature and which do not. So the ones with an OH feature are in the blue here, and the ones without are on the brownish here, and then ones where there was no measurement are the black. But again, it looks like roughly equally split between those with OH features being bright or not, and then those that are dry again being bright or not. So there's no obvious trends here in any of these other properties. So I do want to take a second here and talk about bifurcated radar echoes, which at the time just mystified us, but I think is starting to become a little clearer what's going on, especially with our recent work on Psyche. So most of the data that we get from the M-class asteroids was pretty low SNR. We didn't have enough signal to noise to be able to make the pretty radar images that you see, especially with the near Earth population. However, those, the data was enough to estimate the radar echo power, which was what we used to radar albedo. We could also see a spread. So the way this works is we send out a pulse of a uniform frequency, and let's say 1,000 hertz, just for a number, but it's obviously different. But then it hits the asteroid and reflects back to Earth. Now, if the asteroid was a sphere and it was not rotating, the echo would be exactly the same frequency once you correct for its orbital motion as what you sent out. So Arecibo, Goldstone, they all automatically correct for the orbital velocity, the Doppler shift due to that. What they don't correct for is the spin. So if an asteroid is spinning, part of the asteroid is approaching you and part of it is receding from you as it spins. And so the echo, part of its Doppler shifted up, the part that's spinning toward you, and part of its Doppler shifted down. So the echo is spread in Doppler frequency. And rather than a mono frequency pulse coming back at what we're calling 0 hertz here, we get a spread in the echo. And this can be used to estimate the size of the asteroid, its rotation rate, its orientation. If it's equatorial, you're going to have a bigger spread than if it's a polar view. If it's rotating faster, you're going to have a bigger spread than if it's rotating slowly. But the canonical shape of these echo pulses that you receive are more like Gaussian kind of shape. What I'm showing you here is a variety of examples where we saw this in almost every bright radar asteroid that we observed. We have multiple pulses, often these bifurcated, two wings, sometimes multiple. Here's one with 4 in Dina. Lydia, it's very obvious. Now, one way to generate something like this is if you have say, a binary asteroid or a contact binary. So Cleopatra would give you something like this. But the vast majority, in fact, I think Cleopatra is the only one that I know of that's contact binary. The rest of them have pretty low light curve amplitudes consistent with more or less equant shaped objects, not spheres, but not Cleopatra's either. So you have to explain this some other way. And at the time, we kind of grasped for explanations, and the one that came to mind at the time was, craters or large flat areas or something odd with the shape. However, we got this image of 779 Nina. This was one where we had enough signal to noise to try and get the delayed Doppler image. So on the left is the unprocessed, or not unprocessed, but not enhanced. So Nina's in here somewhere. And you see these 2 bright echoes that would correspond with the 2 lobes that you saw on either side of 0 Doppler. On the right here, I've stretched it. And so if you look carefully, you'll see this kind of crescent moon shape, which is the classical radar echo shape that you would see from a spheroidal type of object. However, you had a bright area here and a bright area over here, which show up really nicely here. So what this is telling us is that although Nina is roughly equant, it has places on the surface that are extremely radar bright. Now, the rest of the asteroid, at different orientations, you didn't see these. It would be moderately radar bright, but in a few orientations, you really get these huge returns, which give you these very bright radar albedos. I'll come back to that in a minute when we look at some of the others. So I'm just going to take a minute and look at some specific asteroids and maybe put them in context with what I mentioned earlier here. So I copied this wholesale from Wikipedia, and I trust it because I wrote it. It's a table in the M-class asteroid entry anyway, where I took the bulk density measurements that had been published for all the M-class available anyway. And I also put the radar albedo there, again, based on primarily the work we've done, and then the method that the bulk density was estimated. And so the ones that are most believable are the ones where you have a spacecraft flyby or a moon orbiting. The ones that are a little trickier are if you're just using what's called the ephemeris method, where you can see the slight variations in its orbit caused by nearby large asteroids. Now, Psyche would be the exception to the ephemeris method being kind of dubious, because it's been the subject of a lot of work, and I think they've really narrowed it down nicely. So that value is probably quite trustworthy overall, and it's consistent with all the others as well. But you will notice that the bulk densities, this is for the asteroid as a whole, range from roughly 3.5 to 4.5. Antigone's kind of a low end, but it's got a huge error bar on it. Cleopatra, 3.5, Calliope 4, Hesperia 4.5, and so on. These are not what you would expect for metal cores, which would be 8. And that's been the conundrum here with Psyche lately. They're consistent with Psyche. So just looking at Psyche, I mentioned this earlier in the opening slide. This is the new shape model with the albedo on the top. I'm just briefly going to go through the data sets that we used to generate this so you can see how much effort's been put into this model. These are radar delayed Doppler images that were taken by us in 2015. And we were able to get a full rotation of Psyche. So all of these are in column format, the ones I'm going to show you. Here you have the radar image, delayed Doppler. This is the shape model at the proper orientation, and this is a synthetic view, what this model should generate to the radar. And so you can compare these directly, and the closer these look, the better your shape model. But overall, I would say, this is we've done a pretty decent job with this. This is a southern mid-latitude view, so we're seeing more of the South Pole. These data were acquired by Catherine DeClear a couple of years ago, and she showed me, and I was like, my jaw dropped. Fantastic images taken at the Atacama Large Millimeter Array, the ALMA Observatory. Now, these are thermal images, but they're at 1 millimeter. Okay, so they're well beyond thermal infrared, but they're still thermal. And again, the images, her images are on the left, because you have this huge spread of telescopes, you can get, decent resolution, which is why you have these nice images. And then our shape model at the same orientation here, and we got about, or she got about 60, 70% rotation. Severio's here, Cambione, he's a co-author on this paper.
Yeah, it was 2/3 of the rotation. Yeah.
Yep. These are a subset of data taken by Pierre Vernazza. He's got a long-term project with the Very Large Telescope. Fantastic instrument, and has been looking at large main belts, a variety of them, but of course, a lot of time spent on Psyche. 2018 on the left, they got a nice northern polar view. So these are their images, they're processed, but and here are our shape models for comparison. These are 2019 pictorial view here on the left, and shape model on the right. And then finally, well, not finally, but these are Keck AO images that Drummond et al. Got in 2015 that we used in our 2017 shape model. And these are images taken in 2020 by, again, Catherine DeClear, and we didn't use them in the shape model, but we did predict what they would look like, and I'm putting them here, and you can see the shape model looks really, really good compared to the data they took. And finally, I'm a big fan of occultations because it's hard to fool, a star winking out or not. And the 2019 occultation shown on the left, fantastic aspect, equatorial, right down the intermediate axis, and really nailed down the size along the c-axis of Psyche and the shape pretty nicely as well. And then 2010, there was a less well-covered occultation, high southern mid-latitudes, but this also helped constrain our A and B axes on the shape model. And here's the latest model, and I put this 1%, plus or minus 1%. I'm comfortable saying that, these dimensions are good to 1% at the 1 sigma level, so the 67%, confidence level. I think that we're within a few kilometers either way. And presented this data, the Psyche team, and there's another model using overlapping data sets produced by Ferre et al. And Bifurcated et al. And our model sizes and shapes are pretty much spot on. We differ in some of the secondary features on the surface, bumps here and there, but the size, the gross shape is pretty much identical. This was the final picture in the paper for that shape model, and I use it because I'm going to come back to the bifurcated echo point that I made earlier. So this is the global model of Psyche. Optical albedo is shown in color. This is the Bifurcated et al. Optical albedo map. And so their model ranged from optical albedos of 20% brighter than the mean and 20% darker than the mean. And then we put on top of that where our individual radar observations were. So these dots represent the centers of our radar, sub-radar centers. We did the experiment in 2015, 2005. And bigger dots mean a brighter echo, and smaller dots here, less than 0.3, they're all within 0.25 to 0.3, which you may remember from the earlier slide is still almost twice as bright as your standard S and C class asteroid. So even where it's not particularly bright, Psyche is still twice as bright as your standard main belt asteroid. But when you get to these areas, it's like, ringing bells, just really, really high echoes. And we found what appears to be a rough correlation. It's crude, but a correlation between bright areas and bright radar echoes. So we suggest in that paper that there's this correlation in optical and radar albedo. But I think perhaps more importantly is that, there's parts of Psyche that aren't particularly radar bright, and there's other parts that are very radar bright. And so back to that picture of Nina and those bifurcated echoes, I think that it just kind of hammered home here that what you're seeing on Psyche maybe explains that better, that what we're not seeing are particularly, weird features or craters or shapes or anything like that, but what we're seeing are places where you have, high density material, metals exposed, but it's exposed in patches. It's not uniform around the object. So finished Psyche. I'm just going to quickly run through the rest, the 2 or 3 more of these, and I'll be done. This is fantastic imagery from Rosetta of Lutetia, and I've said this a couple places. The background albedo, radar albedo for Psyche is about the same as the radar albedo for Lutetia. And when you look at Lutetia, you see what looks like, at least superficially, like a traditional silicate regolith, but we know it. The radar tells us, and then the spectral analysis suggests that it's got a fairly high metal content, maybe not super high, but elevated. I think this is something what we're probably likely to see when we get there, but the difference will be there are places on Psyche where you will see something very different that to the radar is showing up as it's very bright. Maybe it's volcanic flows, these ferrovolcanic flows, maybe it's exposures of the core, from the fiducial model that the team is starting with. I mean, that would be a perfectly valid explanation as well. We did get a little bit of radar data from Lutetia back in 2004, Steve Ostro gave me these to work on, and I tried to make a shape model, but I couldn't get anything that I was happy with. It was too ambiguous. We're looking down the pole, the North Pole, basically, of Lutetia, and there's too many ambiguities to get a good shape model, so we never went further. But you'll see Lutetia still has this, relatively high bulk density. This is a really intriguing. Calliope, and we go back really quick. Calliope, you see, has this high bulk density, and it's probably fairly secure because it has a moon. So the mass shouldn't be any, huge variations in it. The shape models published by the Light Curve, the Dammit website, and they have some AO, and I'm actually working on a shape model with Catherine Servioni right now, so we'll see, but I think the shape model is probably within a few, kilometers or so of being accurate, the size anyway. So this number is probably pretty accurate. But the radar was 0.15. That's like an S class or C class. It's not radar bright at all, which confuses me. And to make it even more confusing, Catherine and Serio got these other ALMA images that have yet to be published, but I want to point your attention to the brightness temperatures here on the right side of each of these images. This is Psyche, and its brightness temperatures are around 100 Kelvin, and it should be about 180 Kelvin, I think, maybe, or so, which means it has a fairly low emissivity, which is consistent with the high metallic content. The rocky stuff has emissivities of about 0.9. Metals are 0.6, 0.5. Over here, for comparison, Juno, a stony S-type, its brightness temperature is around 250, which is right around where you would expect, an emissivity of about 0.9 for in that location of the belt. So this is what you would expect. But then you go to Calliope, and it's got this modest radar albedo, and its brightness temperature is about like Psyche's. So it's got a high density, it's got a high emissivity. The only thing I can think of right now is the Calliope data were taken pre Arecibo upgrade. Now, Patrick may correct me here. I think we got one other radar observation, but it was only one, and it wasn't significantly different. So I don't know what's going on here. That one is a real outlier to me, and we'll have to take some thought. Very briefly, Cleopatra. I just want to point out something from the paper for the shape model. Again, these are radar images on the left, shape model on the right, and this is from two different encounters. So these encounters, as you can see from the orientation of the asteroid at the time they were taken, are equatorial. So here's the spin axis. So we were looking along the equator of Cleopatra as it rotated. And if you look over here at the radar images, it's like stealth. There's nothing there, or maybe a little dot here and there where pieces are radar bright. At other aspects, this is when we were looking more or less in the southern mid-latitudes. You see a lot of radar echo, especially places where it's extremely high, much like we were pointing out in the other asteroids. So there's a lot of variability on Cleopatra. Along the equator, it looks like a regular, silicate kind of rich asteroid, whereas from the South Pole, it looks pretty radar bright. And so there must be exposures, large exposures of metal in the southern part of it. And if you look at the shape model, it's better maybe here. The southern part of Cleopatra is really beat up, large craters there. So it may be that portions of the core are exposed, or maybe the volcanic model. This whole asteroid is kind of a confusing one anyway, because it's bizarre to think about two metal objects coming together, two objects like Psyche coming together and making a contact binary. This one, it's an oddball, to say, understatement. And then the last one I really want to look at is hang on, I'm sorry, President. 785's with Taana is a small asteroid, and it's the CB that we looked at. It was in Tholden's M catalog, so we looked at it. It has the largest radar albedo variations of any target we saw. So this is an example where you have its radar echo at 100 degrees rotation. So that's relative to some arbitrary zero that we set. So here you get a really strong echo, and it just goes away. And then at this rotation, 212, it's back. And then it's there, and then it goes away. And so it ranges from 0.1, which is really low for an asteroid, to 0.6, which is about as high as any that we've seen. So, you know, we called it metal rich at the time. We weren't sure what was going on. Maybe its shape was bizarre. We observed it again in 2013. These were taken in 25 and saw no variation like this at all. Most of it looked like this in 2013. Now it was at a different aspect. So instead of seeing, say, northern mid-latitudes, we might have been looking equatorial or something like that. We were 40 degrees, 50 degrees away from the position. But again, I think this just reinforces what seems to be coming clear, is that there are patches on all of these where you have evidence of high concentrations of metal on some of these, and other orientations where there's nothing evident. All right, so my conclusions and takeaways here. M-class asteroids are uncommon, roughly 5% of the main belt population, approximately half, and I put a star there to remind me of something, are radar bright, suggesting high concentrations of metal. And I say half because a number of the targets we looked at, we only had a few echoes from. So if we had full rotations at multiple aspects, we might have been able to say more confidently, but some of them we may have just been looking at the wrong place at the wrong time. The other half seem to be elevated in metal, much higher than an S and C class, but not quite up to the standards of these others, radar bright. We can find no obvious correlations with radar bright behavior with the SMAS class, the mean optical albedo, the size, the rotation period. All of the radar bright asteroids display behavior suggesting that the source of this radar brightness is concentrated in patches over an otherwise what would be metal enriched regolith, but they're not homogeneous by any means. They're very heterogeneous. All the measured M bulk class bulk densities are intermediate between pure metal and pure rock. And the two models that seem to make the most sense, maybe we'll learn more when the Psyche mission gets there, I hope. Core plus thin crust and mantle of reduced silicates, either with some exposed core or maybe exotic flows on the surface, or potentially we're looking at chondritic, unmetamorphosed objects with enrichments of metals in some places. And although I'd like to be able to say if the M class represents a single kind of object or multiple species, right now I don't think we can. It's too soon. So I will end there, stop sharing, and apologize if I went over time. And
oh no, it was great. Thank you so much, Mike. That was a fascinating talk. So we'll open up for questions now. We've got a few minutes till the end of the hour. So if you have questions, feel free to type them into the chat box. Alternatively, since we're a little pressed for time, you can also raise your hand and I can call on you, and we'll alternate between those. While people are getting those ready, I think we have a couple of questions and comments in the chat box that were entered throughout the talk. Some of those early ones were addressed in the talk, but let's see. So your doppelganger, Michael Shepard, had a question about the rotational rate of Psyche and if that affects your potential compositional interpretation.
Well, Psyche is one of those fast rotators, roughly 4 hours, and it has no effect on the potential composition that I'm aware of. Yeah, but it's a pretty fast rotator.
In there, we had a comment from Patrick Taylor. He says, we're working on a Green Bank VLBA radar system.
Green Bank, that's right. They're going to put a transmitter at Green Bank, I think. That's right.
Let's move over to Saverio Cambioni, who's got his hand raised here. You can unmute.
Yeah, thank you. The great talk, really great collection of data. And So I had actually two questions. The first one is that did you look if there is any trend between the properties and semi-major axis of the bodies? And the second one is what is the current explanation for the x-axis of the periods between 4 hours and 6 hours?
I don't know for the second, I don't know what the explanation is, or if there's a good one at all for the rotation period. Honestly, I have no idea. I've heard people speculate on it. Maybe someone here has a better idea. I don't think I can comment on that. And the first question I missed, I'm sorry.
Yeah, sorry. I was asking if you look at possible correlations between the semi-major axis of the the distance with respect to the sun and the and the properties that you were discussing.
I did not do that here, but one of the papers I showed was Lindy Elkins' Tanton paper, the recent one on potential models for Psyche, and they have an outstanding discussion in there where they went and took all the SMAS classified asteroids, and they did exactly what you're talking about. And they found very intriguingly that the M class seemed to have an affiliation with the outer solar system. I'm sorry, not the outer solar system, the outer main asteroid belt, suggesting that they're more likely than not came from that region rather than what had been proposed, the inner solar system, which seems kind of, backwards from what has traditionally been thought. I thought I saw her here. She might be able to address that. I did not do actually I did do it, but I didn't show it. I didn't find anything that was worth anything more than randomness. When I took the 30 samples or 26 samples here and looked for semi-major axis, I didn't see anything. And the other thing I got to be careful of here is that, there's a bias effect with the radar. We could only see things that were relatively close because of the rapid fall off in the echo power with distance. So preferentially, we're looking at things that were closer to Earth at the time, and we really couldn't, look at anything that was in the outer part of the main belt very easily. See any correlation between density, optical albedos? You want me to answer that, Sam? The correlation between?
Yeah, I'll read it off so people can see it. Do you see any correlation between density, optical, radar albedos, and the presence or absence of silicate in the 0.9, 1.9 micron features in the reflectance spectra of M types?
I will say no, and I'm basing that primarily on the plot where we plotted the radar albedo and the classification in the bus or SMAS scheme. So those spectra would be the ones that would have evidence of any kind of silicate features. Now, there's not a lot of, I don't know how many of those also are in the bus de Mayo scheme, which would extend out to the 1.9 micron. But to my knowledge, there is no correlation between the radar and that feature.
Okay, we've got missed over a couple of questions here, and I think that might be all we have time for. Patrick Taylor is asking, have you tried going back to Lutetia data with the known shape and spin state to see how they match?
No, I haven't. It's on my probably list of many things to do.
All right, we'll stay tuned for that then. The last couple of questions are from Xiao Dong Wang, and they're asking, what is the origin of OH on an asteroid surface?
Well, I mean, there's some that is implanted by the solar wind. I know the moon, and I presume on the surface of some asteroids, there's also presumably exogenic if you have low velocity collisions between something with OH, a primitive asteroid, and an M type. You might leave behind a residual presence, and I think they saw something like that on Vesta. And then there's this recent paper by, I forget his name, but they did high energy impact experiments on metal surfaces. And they found that if they even high velocity collisions onto metal surfaces that a glass was formed. And if the impactor had hydration, it was hydrated, then the glass that formed showed evidence of hydration features, which is an interesting finding. If Psyche were a core, you could explain the hydration features just as high velocity collisions with small, carbonaceous hydrated asteroids on the surface, leaving behind a glassy kind of patina. So there could be a lot of reasons for it.
Interesting. So even the patchy the concentrations of metal could still have some OH signatures in it. That's fascinating. Okay, we got maybe time for one last question that's squeezed in by Flora Paganelli. Got in late, so I'm not sure. Wondering if you test tricorrelations based on a ratio power spectra.
I don't know what that means.
I don't either, so I guess not. On that note, if there are no more questions, you can also send messages in the chat. We can forward those on to Mike if they don't make it in time. But let's give a virtual hand for Mike. That was a really, really interesting talk, and we're grateful for you coming to our seminar today. Thanks so much.
Thank you for inviting me. I appreciate it.
Thanks for being here, everybody, and we'll see you all next week.